Okay. Now we move on to the first section after the introduction, the separation of variables. So basically, we are trying to solve differential equations by hand. Okay. So just a quick reminder, the solution of differential equations, when I say ODE, I mean ordinary differential equations compared to PDE, which involves partial derivatives. Okay. If you only see a differential equation, you look for the general solution, which can involve a constant. Okay, but if you solve an initial value problem, we will write IVP from now on. You look for an initial condition. So you solve for the general solution first, and then you use the initial condition to find out what the constant is. So the majority of solving these two are the same. That is solving the differential equation. But if you are given an initial value problem, you need to do one additional step, that is plug in the initial condition to figure out the constant. Okay. Now the first type we want to talk about are the probably easiest type of differential equations we can solve, which is called separable equations, ODE, differential equations. Okay, and the definition is given by y prime equals gt times hy, which is called separable. That basically means the derivative can be separated into the multiplication of a function of t and a function of y. So for example, separable, the first function is y, the second function is t. So the function of y and t are totally separated. Okay, y prime equals sine y times t. Now from here you can see it's not separable because you cannot do it. It's not sine y times t, which is separable. It's not sine t times y. It's also not sine y times sine t, which is separable. So from here you can see sine y times t is not separable, because it cannot be written into the multiplication of these two things. Okay. Now, why is it doable or useful? Now, let's see how we do it. Okay, let's try the example 1. The one we did was y prime equals ky. So, for example, the first one we did was y prime equals 0.05y. Okay, now what do we have? Well, you want to take the integration, don't you? So let's take it. Okay, that's fine. Then you have a problem. The problem is which one do you want to take derivatives with respect to? Well, which is the derivative here? It's going to be dt. And then what do you know about this one? You don't even know y. How are you supposed to take the antiderivative of yt? Okay, so what you can do is, you can do this. You can first put all the y together on one side, put everything else on the other side with a dt. Now what can you do? You can take this 1 over y times y prime dt, and what is y prime times dt? That is going to be dy. Now the right hand side is very easy to do. Okay, plus a c. The left hand side, if it's with respect to t, it's going to be hard because you got y and a t, and you don't know what y is. But now it's y with respect to y, then that's going to be ln. Of course, for population, we take the positive one, plus c, which is e to the c times e to the 0.05t. Now you can see e to the c is nothing but just any constant. So that's what we're having of how to solve this differential equations. The key is move everything involved y on one side with the y prime, and move everything with respect to t on the other side. So now if you think about why do we require this weird definition for separable, the reason is because you want to move everything involving y on the other side. If it's separable, by the way. If it's not, you cannot do it. And leave only t on this side. And once you do that, you can take the integration. The right-hand side is doable because it's a function of t. If it's a function of t, you take the derivative, antiderivative with respect to t. It's of course doable. Okay. The harder part is the left-hand side. But now the beautiful thing is it's going to be 1 over gy times y prime and dt. And the y prime dt naturally gives you dy. So you can treat the left-hand side as a function of y, and you can treat the right-hand side as a function of t when you take the same antiderivative with respect to dt. That's the beauty of doing separable functions. Okay, so again, y, everything involving y on one side, no t. Everything with respect to t on the other side, no y. Okay. Then, if you take the derivative, antiderivative with respect to t, what's going to happen is the t part with respect to t is going to be fine. The y part with respect to t is not going to be fine. But then, if you merge these two, you have the y part with respect to y, and then it will be fine. All right, that's the idea. Let's try some examples. Y prime equals yt. Okay. Y together, t together. Integration. At the first, it's all with respect to t. But y prime and dt merge into y. And then it's super easy. Again, it's e times something, but this one it doesn't hurt if we just write that thing to be c. Okay. Automatically that includes the positive and negative y part because we do have a positive and negative for absolute value, right? Okay. So that's how we're going to do it. Maybe I'm going over too quick. Maybe I should just write it down carefully. This means y equals e to the 1/2 t squared plus c, which is e to the c times e to the 1/2 t squared. Okay. Note this is always positive, but it can be any positive integer. But your y should equal plus or minus e to the c, e to the 1/2 t squared. Therefore, the whole thing here become any number, both positive and the negative of this. Okay, does it work? Well, let's try y prime. C e to the 1/2 t squared times 2 times 1/2 t, okay, by chain rule, which is c times t times t, which is y times t. So that certainly satisfies the differential equation we just write down. All right, this is nice. Well, what else do we have? Remember the one we couldn't solve because it's too complicated? Okay, that's the logistic. Okay, to solve it is going to take a while, but I will solve the easier ones in class where k and n equals 1. Okay, originally you have a k here, but it's 1. You have a n here, but it's 1. I will solve this one for you, but you will solve the one with the general k and n by yourself as an exercise. Okay, so how do we do it? Well, there's no t, right? If there is no t, then t equals 1. This is the function of t, and it's a constant function. Everybody with y on the other side. Now, you can see the 1 is not a problem, it's just t plus c. All right. The y prime and dt together gives you dy. Therefore, you're just trying to solve this one. To do that, there's no shortcut. You have to go to calculus 2 and calculus 1. Try to see, do you know how to solve the antiderivative of something like this? Partial fraction. I will skip the part. You can verify. It's not our concern here. Where is it? Okay. dy. If you wonder how we got this, check partial fraction. Okay, now we have ln. Okay, we have ln y times 1 plus y. Y times 1 minus, let's see, 1 minus y. 1 minus y here. This is minus. That's why. Okay. Okay. E to the t plus c, which is e to the t times e to the c. Then again, we can change this to c and remove the absolute value because you're going to have plus minus. Okay. Then this whole thing becomes a c, any number. So y equals cet times 1 minus y. Y equals cet minus cet y. Y plus cet y equals cet. So finally, y equals cet divided by 1 plus cet, where c can be any constant. All right, so that's how we solve the logistic. You try it by yourself by going plugging in k and n as general constant, and it's gonna be more complicated, and I can give you the solution for now. For general case, okay, y equals n y0 ekt divided by n plus y0 e to the kt minus 1. Your solution may look a little bit different in terms of format, but if you just plug in the constant and solve everything, you will find they're identical. Okay. For example, if you divide everything by n, you will see you have a thing on the top and you have a 1 plus on the bottom. Okay. So it really depends on how you write it. So, exercise. All right. I think that's enough for separable equations, for examples for separable equations. So the principle is move everything with respect to y on one side, everything with respect to t on the other side. Take both sides of the derivative with respect to t, but then y prime t give you dy, so you can do the integration separately regarding different variables. All right. Some additional examples. And this example is kind of a little bit more special. Okay. And if you just try to do it, it's going to be 1 plus y squared y times y prime dt equals 1 dt. Okay. After that, this becomes dy. So everything so far so good. The antiderivative is not hard either. The problem comes with, after that, what should we do? We should do all the algebra we can such that y equals something involving t, and that's it, and probably c. For this one, you cannot, simply because this algebraic equation is not solvable. And for us, it's no problem. Plug in a t, you can still find y, so just keep your answer that way. And I think it's not surprising that we call this the implicit form of solution. So just some ideas for you to show that, to show you, sometimes it's nice if you could write everything in this way, but sometimes you may have to stop at the implicit solution. Okay, otherwise, it's simply just not solvable. Okay. Some other time, you can solve something like this. Okay, it's separable. So far, so good. Now, still good. If you go ahead and try it, you will find actually every ideas work smoothly except for you just don't know how to do the antiderivatives. Okay, impossible. But not impossible because the differential equation isn't impossible. It's impossible because the integration is impossible. So from here you can see, when you try to solve differential equations like this, we can at least say one thing. Okay, that is, as long as the integration is doable and it's separable, then you can basically solve the differential equation using integrations. But through the process, a lot of things can go wrong. Number one, it's not separable, so you cannot set up the integrations in a nice way. Fail. Number two, you solved it, but you just cannot solve the algebraic equation. It's not fail, but your solution has to be given into an implicit form. Number three, you set up everything right. It is separable, but you got stuck with doing the integration. So anything can go wrong. Nonetheless, that's the first time we're doing it, so it's not too bad. All right. Second thing. Okay. Sometimes you may have missing solutions. Okay. And we can do a simple example. Let's say, okay, and the example we are going to give is y prime equals y squared. This time we want to go ahead and try to solve for a initial value problem. y0 equals 0. Okay, how do you solve that? Well, separable. So y prime over y squared equals 1. 1 over y square y prime dt. Let's give me dy equals 1 dt t plus c negative 1 over y. Okay. So what is y? Y is negative 1 over t plus c. All right, now it's time. It's time for us to plug in 0 and get 0. This implies what? Implies 0 equals negative 1 over 0 plus c. C equals does not exist. Okay, so you solved it, and you find that all the solutions should look like this. But then you plug in the initial value, you find it's impossible. Therefore, there's no solution to the initial value problem. Because I did find a solution, but the initial condition and the solution format cannot be satisfied at the same time. So no solution. Okay. think the calculation, you can do it by yourself. It totally makes sense. But now, let's just look at this original thing again. Is there a solution that satisfies this? And at 0, it's 0? Of course. The solution is given by y equals 0. Y prime is also 0, so of course it's y squared. And also at 0, of course it's 0. It's 0 everywhere. So clearly this one has a solution. So what's going on here? That means when you try to solve the whole thing through separable equation, you somehow missed. You said no solution, right? But somehow you missed this solution here. So this is not right. This is correct. Okay. When did you miss it? That's the moment when you divide y squared on the other side, because you can only do that when y is not 0. So if you did that, automatically you're basically excluding the case that y equals 0, which in this case, it happened to be one of the solution. Okay, so that's one warning for you to do. When you have y prime equals gt hy, it looks great if you just do this. But now, what can happen? What if hy equals 0? Okay. That will give you missing solutions. So if I were you, once I finish doing all these kind of things, I may go back and check really quickly. Will the one that will make hy equal to 0 also possibly a solution? In this case, it is. Then I need to add it back. Okay. In other cases, maybe it's not. All right. Number 4. One applications. What is it? Well, let's talk about skydiving. Do you know the formula of skydiving? Well, probably not. Okay, you got a guy. Well, let's call this a guy. Who is doing skydiving? Okay, I will let yt be the height. Okay, at t. Therefore, vt, which is y prime t, will be the velocity, and at equals y prime prime t equals the acceleration. So according to F equals ma, what should you have? You should have m and a, depending on which way you want to do it, equals F, and F is nothing but mg. So that's the force. Where mg come from? The gravity. Okay, how do you call that thing? That thing is going to be free fall. It's not skydiving, it's suicide, right? That basically means you just go down without a parachute. So this is actually not free diving, it's free fall. So how do you make it free diving? What you do is you do free fall for a while, but eventually what you want to do is, not free diving, skydiving. You want to carry a parachute such that you can add an additional force actually towards up. So if mg is positive, this one is going to be negative because it's pointing up. Okay, and that is going to be what you get from the air resistance thanks to your parachute. The rest is just a matter of how do you calculate the force provided by the parachute or provided by the air. And turns out in experiment we can try, it is proportional to the square of the velocity. Okay. Therefore, in order to solve this, I probably don't want to write this one as y prime prime. Instead, or we can, okay. That is one way of doing it. But for this one, I'm more interested in the velocity. Therefore, I can change it a little bit. This one looks a little bit nicer. From here, you can see, okay, this is probably impossible. I don't want to do a second order derivative. But you can change all the second order derivative into the first order derivative if you just focus on the velocity instead of the displacement. That will be the skydiving formula. Okay. Do you know how to solve it? Well, okay. These are constant, so let's ignore the constant. Constant. That's basically something look like this, where the constant are changed a little bit, right? Now, can you see that this is actually separable? Okay, and then you have the v. This one become 1 plus v, 1 minus v. Using partial fractions, you can solve it. So this becomes solvable. Using separation of variables. I will leave it to you. I have the answer here on my... Actually, I don't have to give it to you. You can get it from Wolfram easily. Okay? I just want to show you the examples when you finish. Yeah, I actually... okay. I wrote the answers to be here. But now what we have is we start from no velocity at the beginning. So we basically just do a free skydive with no initial speed. And the number of points 100. Do it in 10 seconds. Now the final answer is going to look like that. So what happened? You keep diving and you keep accelerating until you are fast enough such that the air resistance equals your gravity, so they balance out. Therefore, your velocity stay unchanged because you don't have force anymore. That will happen when your mg equals your kv squared. That will happen when your gravitational force matches your air resistance. Before that, because you're not quick enough, you're not fast enough, your gravity is actually going to be bigger than the air resistance. All right? So that's what we're going to have. Now, what we're going to do is we're going to design a parachute. It will actually make sure that you hit the ground, or you when you hit the ground, you will actually reach it at 10 miles per hour, whatever units you pick, and maybe it's safe. Now, what do you want to do? You say, what about I have a heavier person? Okay. Can you see that? As you make the person to be heavier, the final speed is going to be bigger. Therefore, for people with higher weight, you probably want to use a, you want to use a parachute with a stronger air resistance. Otherwise, something safer for a light person is not going to be as safe as some people, if you use the same parachute for a light person, it may not be safe for the heavier person. Okay, that's one observation we have. Now, a second thing you can think about is, okay, again, if you change your mass to be 5 and your keep your mass, now you actually build the parachute to be stronger, to increase the K. A bigger parachute is going to give you a bigger K. That means bigger, bigger air resistance. Okay, now increase K. Can you see that increasing K is going to greatly reduce the final speed that you hit the ground. Okay, so if you make it too big, it's going to be boring for you to do the skydiving because basically you're just going to go down at a very, very slow speed, which is not exciting. Okay, so the designing of parachute in general is just trying to adjust for different people with a different weight. How should I actually manipulate the K so that the whole thing stay exciting, meanwhile safe? Okay, and then you write those kind of specifications on the instructions of the manuals, or maybe the instructions of the parachute when you sell it. And based on this very simple equation. Okay. How do we know that it's kv squared? Well, you can derive it from very simple laws, or you can simply just measure it in some kind of experimental facilities. Okay, so separable equation is actually very common to see in real life. Again, the key is try to make sure that you recognize the separation. That is one function of t and one function of y. All right, that's all we have for this.